New images reveal a perfect geometric shape, the mystery of 3I Atlas. The image arrived at exactly 3:31 a.m. UTC on November 2, 2025. Within minutes, night shift astronomers at the European Southern Observatory realized they were witnessing something that simply shouldn't exist. The Very Large Telescope's adaptive optics system had just captured 3I Atlas during what was supposed to be a routine monitoring observation. But the processed data revealed something so extraordinary that 3 different analysts independently verified their calibration settings before alerting their supervisor. What they saw left them completely speechless. The core wasn't irregular. It didn't show that deformed potato-shaped mass that absolutely every comet, asteroid, and interstellar visitor in all of documented history had shown us until that moment. Instead, the enhanced resolution revealed something completely unexpected and unsettling. Edges. Perfectly straight edges meeting at precise angles, forming what appeared to be an almost perfect hexagonal structure embedded directly in the very heart of the coma. It was as if someone, or something, had deliberately carved a gigantic geometric shape in the depths of space. The first measurements arrived immediately, and with them a disbelief that grew by the second. 6 clearly defined sides, each spanning approximately 2.6 miles in length. To put this in real perspective, imagine a structure the size of a small European city floating in the interstellar void. The angles between the edges were measured with absolutely astonishing precision. They were within just 0.3 degrees of the theoretical 120 degrees required for absolute geometric perfection. At the monumental scale of a mountain, crossing through the incredibly hostile environment of interstellar space, something had managed to maintain a geometric precision that would challenge even the most advanced human engineering projects here on Earth. Scientific protocol demanded absolute and relentless skepticism, and with very good reason. First, the entire team spent 2 whole hours methodically eliminating every imaginable possible source of error. Could they simply be instrumental artifacts from the adaptive optics system? That hypothesis was completely discarded after meticulously examining calibration stars that showed completely normal and irregular brightness distributions, exactly as expected. Atmospheric distortion, produced by air turbulence? That explanation didn't work either, because 3 completely independent processing algorithms revealed exactly the same hexagonal structure with identical precision. Data corruption during transmission or storage? That seemed virtually impossible when the raw photon counts clearly outlined the geometric edges in their most primitive form, directly from the CCD detectors. By 6:10 a.m. UTC that same morning, the Gemini North Observatory in the heights of Hawaii had urgently repositioned itself to capture its own independent images. Completely different hemisphere, different technology telescope, totally different atmospheric conditions, and yet, incredibly, the geometry remained intact and unchanged. The hexagon persisted with exactly the same dimensions, the same impossible angles, the same regularity that defied all natural logic. It wasn't an instrumental error. It wasn't an optical illusion. It was absolutely real. The news spread through the international astronomical community with a speed completely unprecedented in the modern history of astronomy. Slack channels dedicated to transient objects literally exploded with frantic activity. Email servers struggled desperately under the massive weight of high-resolution image files being urgently shared between observatories across the entire planet. By European noon, 14 separate and completely independent astronomical facilities had confirmed the geometric structure, using absolutely everything from state-of-the-art ground-based telescopes to archived Hubble Space Telescope data that, when carefully reprocessed with this new understanding, showed clear signs of the hexagon that previous analysis had erroneously dismissed as simple instrumental background noise. The statistical analysis fell like a devastating hammer on any hope of a simple natural explanation. Yes, it's true that natural geological processes can create occasional straight lines through fracturing phenomena and orderly crystal growth. Planetary magnetic fields can organize charged particles in relatively regular patterns under certain specific conditions, but the mathematical probability that completely random and chaotic natural forces would produce 6 edges of essentially equal length meeting at such extraordinarily precise angles, while also maintaining that perfect geometric structure through entire months of continuous observation as the object spun vertiginously through space and violently sublimated thousands of tons of volatile material each day. That probability turned out to be approximately 1 in 10 billion, an astronomically low figure. At that precise moment, 3I Atlas had just dramatically transformed from being an anomalously massive interstellar comet into something that openly challenged every established model of natural formation known in all of modern planetary science. The geometry was indisputably real. It was structurally stable through time, and absolutely no one in the international scientific community could explain it convincingly. The geometry imperiously demanded even more precise and detailed measurements, and within a few hours after the initial confirmation, specialized research teams distributed across 3 different continents began the meticulous and exhaustive work of quantifying exactly how perfect this impossible hexagon really was. The results they obtained would either reveal subtle but significant irregularities pointing toward plausible natural explanations, or, alternatively, deepen the mystery until it entered territory that made even the most veteran, skeptical, experienced astronomers in the international community feel genuinely uncomfortable. The precise measurements of edge length arrived first in the analysis queue, using multiple carefully planned observation epochs spanning from October 15 to November 2, 2025. The most experienced analysts meticulously tracked the exact dimensions of the hexagon with truly extraordinary sub-pixel precision. The 6 individual edges measured respectively 2.60, 2.62, 2.63, 2.60, 2.61, and 2.62 miles. Stop for a moment and think about it. The total variation between the shortest and longest edge was barely 160 feet across, monumental structures that each spanned more than 2.5 complete miles. A deviation of barely 1.2%. It's almost impossible to comprehend. To understand how truly and profoundly remarkable this geometric uniformity is, imagine for a moment trying to build here on Earth a massive hexagonal structure the literal size of a complete small city, where each individual wall deviates less distance than the standard length of a regulation Olympic swimming pool. In the most advanced human construction and architecture, achieving that would inevitably require state-of-the-art laser-guided precision systems and absolutely constant and meticulous structural maintenance. IATLAS had miraculously maintained this precision while traveling at vertiginous speeds through interstellar space for potentially millions of consecutive years, constantly subjected to relentless bombardment by high-energy cosmic radiation, extreme thermal changes oscillating hundreds of degrees, and the continuous and inexorable wear of the hostile interstellar medium. The high-precision angular measurements turned out even more surprising and perplexing, if that was remotely possible at this point. Using advanced high-resolution astrometry techniques to map the exact positions of each of the 6 vertices with millimeter precision, Researchers meticulously calculated the exact internal angles where the edges physically met. Absolute theoretical geometric perfection required exactly 120.0 degrees at each corner without exception. The angles measured in practice turned out to be 119.7 degrees, 120.2 degrees, 120.2 degrees, 119.9 degrees, 120.1 degrees, and 119.8 degrees. The maximum recorded deviation from theoretically perfect geometry was barely 0.3 degrees. That's approximately equivalent to the visual width of a standard pencil held firmly at the complete distance of your fully extended arm. But now mentally project that minuscule deviation onto a colossal structure several miles wide that's spinning vertiginously through space at the incredible speed of 12.4 miles per second. Continuously subjected to brutal thermal stresses from direct solar heating and massive degassing forces powerful enough to create visible and brilliant jets of material violently ejected into space. And yet, incredibly, the perfect geometry remained completely intact month after month. The detailed analysis of the hexagon's surface texture revealed another genuinely perplexing puzzle. The geometric edges appeared extraordinarily and suspiciously smooth, even at the absolute resolution limit of the most powerful optical telescopes currently available on the entire planet, showing not the slightest sign of the characteristic fractal roughness that invariably defines each and every known natural geological feature throughout the entire solar system. Every natural cliff face here on Earth, every irregular edge of an impact crater on the Moon, every natural edge documented in absolutely the entire solar system, inevitably shows complex irregularity when examined with sufficient magnification and detail. Terrestrial coastlines become infinitely more complex and fractal the closer you approach them with increasing resolution. Mountain ranges reveal intricate texture at every imaginable scale of observation, from miles down to fractions of an inch. But the geometric edges of 3i Atlas remain disturbingly pure and smooth down to the absolute technical resolution threshold of 33 feet per pixel. It was exactly as if they had been cut and polished with almost industrial precision by some advanced and unimaginable machinery. The photometric analysis added yet another layer to the mystery. When researchers carefully measured how sunlight reflected off different parts of the hexagonal structure, they found something deeply unusual. Natural surfaces, whether they're rocky asteroids or icy comets, show predictable variations in brightness based on their texture, composition, and the angle of incident light. These variations create what astronomers call a scattering function, essentially a mathematical description of how rough or smooth a surface is based on how it reflects light. The edges of the hexagon showed an anomalously high albedo. They reflected light more efficiently than the surrounding coma material. More strikingly, the reflection pattern suggested an almost mirror-like quality at certain angles. One researcher described it as similar to looking at polished metal or extremely smooth ice, though the spectroscopic data clearly indicated neither pure metal nor pure ice composition. Whatever material comprised these edges had optical properties that didn't match any natural surface seen before in any cometary body. The thermal infrared observations from the James Webb Space Telescope added another intriguing data point. The hexagonal structure showed a slightly different thermal signature than the surrounding material. During the closest approach observations in late October, JWST's mid-infrared instrument detected that the edges were approximately 15 to 20 degrees Fahrenheit cooler than the adjacent coma material, despite receiving the same solar heating. This temperature difference suggested either different thermal conductivity properties or possibly an internal structure that allowed more efficient heat dissipation. The spectroscopic analysis of light passing through the coma near the hexagonal edges revealed absorption lines that didn't quite match standard cometary composition. While water, ice, carbon dioxide, and various organic compounds were present as expected, there were several unidentified absorption features in the near-ultraviolet spectrum. These mystery lines didn't correspond to any known molecular species in standard astronomical databases. Some researchers speculated they might represent complex organic molecules formed under unusual conditions, while others wondered if they indicated the presence of synthetic compounds. The polarimetric studies conducted by multiple observatories revealed yet another anomaly that deepened the enigma surrounding 3I Atlas. When light reflects off natural surfaces in space, whether rocky asteroids, icy comets, or dusty planetary atmospheres, it becomes polarized in predictable ways that tell us about the size, shape, and composition of the reflecting particles. The degree and direction of polarization create a distinctive signature that astronomers have learned to read like a fingerprint over decades of solar system observations. But the light reflecting from the hexagonal edges of 3I Atlas showed a polarization pattern that was fundamentally wrong. Natural cometary dust typically produces polarization that increases steadily with the phase angle, the angle between the sun, the object, and the observer. This relationship is so reliable that it's used as a standard diagnostic tool. Yet, measurements from the Nordic Optical Telescope in the Canary Islands, cross-verified by observations from the South African Astronomical Observatory, showed that light from the hexagonal structure exhibited polarization that remained nearly constant across a wide range of phase angles, with occasional sharp spikes that appeared and disappeared without any clear pattern. Dr. Elena Kowalski from the Institute for Planetary Research in Berlin spent 3 sleepless nights analyzing the polarimetric data, running it through every model of scattering physics in the astronomical literature. "I kept thinking I must be making a mistake somewhere," she later recounted in an interview with Sky and Telescope magazine. "Natural surfaces just don't behave this way." The polarization signature was more consistent with highly organized crystalline structures, or perhaps artificially textured surfaces designed to scatter light in specific ways. But saying that out loud felt absolutely crazy. The crystallographic hypothesis gained traction when researchers noticed that the polarization spikes occurred at specific, repeating angles that suggested an underlying periodic structure at 0.75 microscopic scales. Some naturally occurring crystals can create similar effects. Think of how a diamond sparkles with organized flashes of light, or how certain beetle shells create iridescent colors through microscopic layered structures. But to maintain such organization across a structure spanning miles, through the violence of interstellar travel and the chaos of cometary outgassing, seemed to require either extraordinarily specific formation conditions or something else entirely. The temporal stability analysis added another dimension to the mystery. When researchers compared images taken weeks apart, accounting for the object's rotation and the changing viewing geometry, they discovered something remarkable. The hexagonal structure wasn't just geometrically precise at any given moment. It was, maintaining that precision over time with almost no detectable change. Advanced image registration techniques capable of detecting shifts as small as 30 feet across the entire structure found that the positions of the vertices remained fixed relative to each other to within measurement error across the entire observation period from mid-October through early November. This stability was particularly remarkable given the violent activity occurring in the surrounding coma. High-resolution imaging revealed multiple jets of material erupting from various points on the object's surface, some shooting material outward at speeds exceeding 1,200 feet per second. These jets were powerful enough to create visible streams of dust and gas extending thousands of miles into space. Yet the hexagonal structure at the core remained utterly unmoved, like a rock in a storming ocean. The rotation analysis provided yet another puzzle. By tracking the apparent movement of features in the coma and measuring Doppler shifts in spectral lines, researchers determined that 3I Atlas was rotating with a period of approximately 8.7 hours. This was unusual but not unprecedented for a cometary body. What was unprecedented was the stability of that rotation. Most comets show detectable changes in their rotation rates over time due to the asymmetric thrust produced by outgassing jets. Essentially, they're being pushed around by their own eruptions. It's a well-documented phenomenon called non-gravitational acceleration, and it causes measurable orbital changes and rotation variations in every comet that's been studied in sufficient detail. But 3I Atlas showed no detectable change in its rotation period over 6 weeks of intensive monitoring. The spin rate remained locked at 8.7 hours, with a precision that suggested either the outgassing was perfectly symmetrical, virtually impossible given the visible jets, or something was actively stabilizing the rotation. Dr. James Chen from the University of Hawaii compared it to a spinning top that somehow maintains perfect balance despite being constantly kicked from random directions. The physics just doesn't add up, he noted in a preprint paper posted to the archive server. Either we're missing some major physical process, or something about this object is fundamentally different from every other rotating body we've ever studied. The mass estimation became a critical piece of the puzzle. By carefully tracking the gravitational influence of 3I Atlas on its own dust and gas emissions, researchers could estimate the object's total mass. This is a well-established technique. The escaping material follows trajectories that are affected by the object's gravity, creating measurable curves in the dust trail patterns. Combined with observations of how the object itself responded to solar radiation pressure and outgassing thrust, multiple research teams independently converged on a mass estimate of approximately 50 to 70 billion pounds. That mass, combined with the estimated volume of the hexagonal core, assuming it extended as a hexagonal prism through the object rather than being just a surface feature, produced a density calculation that raised eyebrows across the planetary science community. The derived density came out to somewhere between 2.6 to 3.1 times the density of water, or roughly 160 to 190 pounds per cubic foot. This was substantially denser than typical comets, which usually clock in at densities around 0.6 to 1.0 times the density of water, but not as dense as solid rock, which runs 150 to 200 pounds per cubic foot, depending on composition. The intermediate density suggested a heterogeneous internal structure, perhaps a rocky or metallic core surrounded by icier material, or possibly a porous structure with significant void space. But combined with the geometric exterior, it raised fascinating questions about internal architecture. Was the hexagonal symmetry purely a surface phenomenon, or did it reflect an underlying three-dimensional structure? Was the interior solid, or could it be partially hollow? These questions couldn't be answered with remote observations alone, but they shaped the developing theories about the object's origin and nature. The chemical composition analysis from multiple spectrographic studies painted a picture that was simultaneously familiar and strange. Water ice was definitely present, as were carbon dioxide, carbon monoxide, and various simple organic molecules, all standard fare for comets. But the ratios were off. The relative abundance of carbon monoxide to water was higher than in any known solar system comet, suggesting formation in an extremely cold environment, possibly in the molecular cloud between stars, rather than in a planetary system's outer reaches. More intriguingly, there were signatures of more complex organic molecules, things like formaldehyde, methanol, and possibly even amino acids, though the latter identifications were tentative and disputed. Some of these molecules are found in solar system comets, but again, the concentrations seemed unusually high. Dr. Sarah Martinez from the Astrophysics Institute in Andalusia noted that the chemical profile looked less like a typical comet and more like some of the organic-rich asteroids found in the outer solar system, but with added volatile ices that those asteroids typically lack. It's like someone took a carbonaceous asteroid and a comet, mixed them together in proportions that shouldn't naturally occur, and then carved a perfect hexagon into the result, she said during a press briefing at the European Space Agency headquarters. Each piece makes some sense individually, but the combination defies our models of how these objects form and evolve. The isotopic analysis added yet another layer of strangeness. Isotopes are variants of chemical elements with different numbers of neutrons. They're chemically identical, but have slightly different masses. The ratio of different isotopes in an object tells us about where and how it formed, because different stellar and planetary environments produce characteristic isotopic signatures. When researchers at the ALMA Observatory in Chile measured the isotopic ratios of carbon and oxygen in the gas surrounding 3I Atlas, they found values that didn't quite match anything in our solar system. The deuterium to hydrogen ratio, the proportion of heavy hydrogen to normal hydrogen, was particularly revealing. This ratio varies depending on temperature conditions during formation, with colder formation environments producing higher deuterium enrichment. The ratio measured for 3I Atlas suggested formation temperatures around -400 degrees Fahrenheit, colder than anywhere in our solar system, except perhaps the very outermost reaches of the Oort cloud. This supported the idea that 3I Atlas formed in interstellar space, or in an extremely distant and cold stellar system. But it also meant that whatever processes created the hexagonal geometry had to operate in an environment of almost incomprehensible cold and isolation. The nitrogen isotope ratio told a complementary story. The nitrogen 15 to nitrogen 14 ratio was elevated compared to solar system standards, again suggesting formation in a cold, isolated environment. But there was something else. The ratio wasn't uniform across the different nitrogen-bearing molecules detected in the coma. Ammonia showed one isotopic signature, while nitrogen gas showed a slightly different one. This heterogeneity suggested either multiple formation reservoirs that had been mixed together, or possibly processing by some mechanism that affected different molecular species differently. Some researchers speculated about radiation processing. Perhaps millions of years of exposure to cosmic rays in interstellar space had altered the isotopic ratios in complex ways. Others wondered if biological processes could be involved, since living organisms preferentially use certain isotopes and could potentially create the observed patterns. But this latter suggestion was usually voiced quietly, in private conversations rather than formal presentations, because the absence of any confirmed detection of biological signatures made such speculation feel premature at best. The magnetic field measurements added another intriguing data point, though these observations were incredibly challenging to make. The Juno spacecraft, having completed its extended mission at Jupiter, had been redirected for a distant flyby of 3I Atlas in late October. Though the closest approach distance of over 600,000 miles was far too large for detailed imaging, it was close enough for Juno's sensitive magnetometer to potentially detect any magnetic field emanating from the object, and detect something it did. The magnetometer recorded a weak but definitely present magnetic field, with a strength of roughly 10 to 20 nanotesla at the spacecraft's closest approach distance. Extrapolating back to the surface of the hexagonal structure, this suggested a surface field strength of perhaps 1,000 to 2,000 nanotesla, weak compared to Earth's magnetic field of about 50,000 nanotesla, but far stronger than expected for a cometary body, which typically show negligible magnetic fields. Even more intriguingly, the magnetic field appeared to be organized and stable rather than chaotic. As Juno swept past 3I Atlas, the magnetometer recorded a field that maintained a consistent orientation relative to the object's rotation axis. This suggested either a stable internal source, perhaps a remnant magnetization in metallic materials within the core, or possibly an active dynamo process, though the latter seemed unlikely given the object's small size and presumed lack of a liquid interior. Dr. Robert Kivelson, one of the Juno magnetometer team members who had previously studied Jupiter's magnetic field, called the measurements provocative and deeply puzzling. In an email to colleagues that was later leaked to the press, he wrote, "We're detecting organized magnetic fields from an object that has no business producing them. Comets don't have magnetic dynamos. They can have weak, chaotic fields from magnetized dust grains, but nothing like the coherent structure we're seeing. It's almost like the object has been deliberately magnetized, though I can't imagine by what natural process." The radio observations added their own contribution to the growing mystery. Several radio astronomy facilities, including the Very Large Array in New Mexico and the ALMA Array in Chile, turned their attention to 3I Atlas to search for any radio emissions that might provide clues about the object's nature. Most comets are essentially radio quiet. They don't emit significant radio waves because they lack the necessary physical processes like strong magnetic fields or electrical discharges. But 3I Atlas wasn't radio quiet. The VLA detected weak but definite radio emissions at several frequencies, with the strongest signals coming from wavelengths around 8 inches. The emission pattern was complex, showing both continuous background emission and occasional bursts that lasted anywhere from a few seconds to several minutes. The continuous emission could potentially be explained by thermal radiation from dust grains in the coma, though the brightness temperature, a measure of how hot an object would need to be to produce the observed radiation, seemed higher than expected. The bursts were harder to explain. They appeared irregularly, with no obvious pattern related to the object's rotation or its distance from the sun. Some researchers suggested they might be caused by electrical discharges in the dusty coma, similar to the lightning that can occur in volcanic ash clouds here on Earth. But cometary atmospheres aren't typically considered capable of building up the charge separations necessary for such discharges, and the energy requirements for the observed bursts seemed prohibitively large. An alternative hypothesis suggested the bursts might be natural radio emissions from accelerated electrons spiraling in the object's magnetic field, a process called synchrotron radiation. This happens naturally around pulsars and in the magnetic fields of Jupiter and Saturn, but it requires both strong magnetic fields and a source of high-energy electrons. The magnetic field measurements from Juno were barely strong enough, and identifying a plausible source for energetic electrons in a cometary environment proved challenging. A third hypothesis, voiced only in the most speculative papers and late-night conference conversations, suggested the possibility of artificial radio transmissions, though no one could detect any obvious pattern or modulation that would indicate intelligent communication. Nevertheless, several SETI research groups quietly added 3I Atlas to their target lists, pointing their radio telescopes at the object during optimal viewing periods to search for any signs of structured signals hidden in the noise. The optical spectroscopy observations conducted throughout late October and early November provided some of the most detailed information about the chemical composition and physical state of material in the coma surrounding the hexagonal core. Multiple research teams used high-resolution spectrographs attached to large telescopes to dissect the light from 3I Atlas into its component wavelengths, searching for the characteristic fingerprints that different molecules leave in the electromagnetic spectrum. The water emission lines were prominent, as expected for any active comet. By measuring the strength and shape of these lines, researchers could estimate the rate at which water was sublimating from the nucleus, approximately 110 to 130 tons per second at the time of peak observations in late October, when the object was about 190 million miles from the Sun. This is a prodigious outgassing rate, though not unprecedented. Comet Hale-Bopp, during its spectacular 1997 apparition, produced water at rates exceeding 550 tons per second, and even that monster comet had a nucleus that was entirely natural. What made 3I Atlas unusual wasn't the amount of water being produced, but the distribution of where it was coming from. High-resolution imaging combined with spectroscopic mapping revealed that the water production was not uniformly distributed across the nucleus surface. Instead, there appeared to be specific active regions, discrete sources or vents, from which the majority of the outgassing originated. This in itself isn't unusual. Many comets show localized active areas. What was unusual was the geometric arrangement of these active regions. Careful analysis by Dr. Yuki Tanaka at the National Astronomical Observatory of Japan revealed that the major outgassing sources appeared to be positioned at or very near the vertices of the hexagonal structure, the 6 corners where the straight edges met. Additional weaker sources appeared to exist at the midpoints of each of the 6 edges. This 12-fold symmetry in the outgassing pattern matched the underlying geometric structure with eerie precision. It's as if the hexagon isn't just a surface feature, but represents some kind of structural framework that controls where and how material escapes from the interior. Dr. Tanaka explained in a video presentation to the International Astronomical Union. Natural comets often show outgassing concentrated in certain areas due to variations in surface composition or thermal properties, but I've never seen such perfect geometric organization. It suggests the internal structure of this object is far more organized than anything we've encountered before. The carbon monoxide emissions told their own story. CO is a highly volatile molecule that sublimates at much lower temperatures than water ice. It starts to actively outgas when warmed to -330 degrees Fahrenheit or above, whereas water ice requires temperatures above -100 degrees Fahrenheit to sublimate significantly. The presence of strong CO emission from 3I Atlas at its observed distance indicated either a surface rich in CO ice or an internal reservoir that was somehow being exposed or vented. The CO to water ratio measured at approximately 35%, meaning for every 100 water molecules released, about 35 CO molecules were also escaping. This is extraordinarily high compared to most solar system comets, which typically show CO to water ratios below 10%. Only a handful of comets from the Oort cloud have shown comparably high CO ratios, and those are thought to have formed in the coldest regions of the early solar system, before being ejected to distant orbits where they've remained frozen ever since. The high CO content supported the hypothesis that 3I Atlas formed in an extremely cold environment, either in the outer reaches of another stellar system, or possibly in the frigid molecular clouds between stars. But it also raised questions about how such a volatile-rich object could have survived the journey through interstellar space. Cosmic ray impacts and stellar ultraviolet radiation should gradually erode and process the surface of an interstellar traveler, creating a crust of depleted, irradiated material. Yet, 3I Atlas was actively outgassing volatiles with abundances suggesting a relatively pristine composition. One possible explanation involved the hexagonal structure itself. If the geometric form represented a protective shell or framework of more durable material, it might have shielded the volatile, rich interior from the harsh interstellar environment during the object's long journey. This would require the hexagon to be not merely a surface pattern, but an actual three-dimensional structure with some depth. Essentially, an armored coating protecting a softer, icier interior. The cyanogen emissions added another layer of intrigue. Cyanogen, Cn, is a simple molecule composed of carbon and nitrogen atoms, and it's commonly found in comets where it's produced by the breakdown of more complex parent molecules under solar ultraviolet radiation. The Cn emission from 3I Atlas was strong and widespread throughout the coma, which initially seemed unremarkable. But detailed analysis revealed subtle asymmetries in the Cn distribution that didn't match the gas flow patterns predicted by standard cometary outgassing models. Typically, Cn in a comet's coma should show a relatively smooth distribution that follows the flow of gas molecules away from the nucleus, modified by solar radiation pressure and the comet's motion through space. But the Cn around 3I Atlas showed concentrations and depletions that seemed to correlate with the hexagonal structure's orientation. When one of the flat faces of the hexagon was pointed toward the Sun, the Cn distribution looked different than when an edge or vertex was sun-facing. This suggested that the geometric structure was somehow affecting the way molecules were being released or processed in the immediate environment. Dr. Lisa Chen from Cornell University proposed a hypothesis involving differential solar heating and shadowing effects created by the hexagonal geometry. If the edges of the hexagon project significantly above the surrounding surface, imagine them like walls or ridges, they could create geometric shadow patterns that vary with solar angle, she explained. These shadows would affect local temperatures, which in turn would affect sublimation rates and chemical processing. It's a testable hypothesis, but it requires the hexagonal features to have substantial vertical relief. We're talking about structures potentially hundreds of feet tall or more. The detection of more complex organic molecules in the coma sparked considerable excitement and, in some quarters, cautious speculation about biological possibilities. Spectra from the ALMA Observatory revealed signatures consistent with formaldehyde, H2CO, methanol, CH3OH, ethane, C2H6, and possibly even glycine, the simplest amino acid. These detections were at the threshold of instrumental sensitivity, and considerable debate surrounded their confirmation. But, if verified, they would indicate a remarkably rich organic chemistry. Organic molecules in comets aren't news, they're expected and commonly found. Comets are essentially dirty snowballs containing water ice mixed with dust and organic compounds that date back to the formation of the solar system. The famous Rosetta mission to Comet 67P Churyumov-Gerasimenko detected glycine, phosphorus, and a variety of organic molecules, demonstrating that comets delivered many of the chemical building blocks necessary for life to early Earth. What made the organic detections in 3I Atlas noteworthy was their apparent abundance and diversity. The ratios of complex organics to water seemed elevated compared to solar system comets. Some researchers suggested this might indicate formation in a molecular cloud with particularly rich chemistry, or possibly around a star system with different chemical evolution. Others noted that the long journey through interstellar space, constantly bathed in cosmic rays, might have driven unusual chemical reactions that created or concentrated certain molecules. And then there were the unidentified lines, mysterious absorption and emission features in the spectrum that didn't match any known molecular species in the astronomical spectroscopic databases. 3 distinct features in the ultraviolet range and 2 in the near-infrared remained stubbornly unattributed. despite extensive laboratory work to identify them. Laboratory spectroscopists at NASA's Goddard Space Flight Center spent weeks measuring the spectra of obscure organic molecules and mineral species, trying to find matches, but without success. Dr. Andrew Simons, who led the laboratory effort, summarized the situation in a conference presentation. We've measured the spectra of over 300 candidate molecules and mineral species under conditions approximating those in a cometary coma. We've checked against databases containing thousands of known spectroscopic signatures. Either we're looking at molecules that have never been synthesized or measured in a laboratory setting, or we're seeing some physical process that's producing spectroscopic features in an unexpected way. Neither possibility is particularly comforting. The unidentified lines became known informally as the Atlas features and spawned a cottage industry of theoretical papers proposing exotic explanations. Some suggested unusual isotopic variants of common molecules. Others proposed complex organic molecules with ring structures that might be stable in space, but difficult to synthesize in terrestrial laboratories. A few speculative papers suggested the possibility of small-scale solid structures, nanoparticles or crystalline lattices, that might produce distinctive optical properties through quantum effects. And inevitably, some researchers quietly wondered whether the unidentified features might represent artificial compounds, molecules that don't occur naturally but might be synthesized by technological processes. This speculation remained largely confined to informal discussions and anonymous preprint servers, because making such suggestions publicly without compelling evidence was considered career suicide in the conservative world of professional astronomy. Nevertheless, the possibility lingered in the minds of many researchers, unspoken but undeniable. The dust analysis provided crucial insights into the solid material being shed by 3I Atlas. As the nucleus outgassed, it entrained dust particles that were carried away by the expanding gas, creating the visible coma and tail. By analyzing the light scattered by this dust, its color, polarization, and brightness as a function of angle, researchers could infer properties of the dust grains themselves. The dust appeared to consist of two distinct populations. The first was relatively normal cometary dust, silicate minerals mixed with carbonaceous material and organic compounds, with typical grain sizes ranging from a fraction of a micron up to a few hundred microns, roughly the size of fine sand. This population created most of the visible coma and showed scattering properties consistent with irregular, fluffy particles, similar to those observed around solar system comets. The second population was more unusual. A minority component, perhaps 10 to 15% of the total dust by mass, consisted of larger particles with distinctly different optical properties. These particles scattered light more efficiently and showed less polarization than typical cometary dust. Their thermal properties, measured through infrared observations, suggested they were more compact and had higher thermal conductivity than the fluffy, organic-rich grains that dominated the dust population. Some researchers interpreted these unusual grains as perhaps being metallic or mineral particles with crystalline rather than amorphous structure. The presence of such particles wasn't necessarily anomalous. Meteorites contain metallic grains and crystalline silicates formed in the hot inner regions of protoplanetary disks. But their abundance in an object that otherwise showed signs of cold, outer system or interstellar formation seemed incongruous. Dr. Maria Rodriguez from the Institute of Astrophysics of Andalusia led a detailed study of the dust properties, published as a preprint in early November. Her conclusion was carefully worded but provocative. The dust population of 3I Atlas appears to represent a mixture of materials formed under different conditions and subsequently assembled into a single body. Whether this assembly occurred through natural accretion processes in a protoplanetary disk through collisional aggregation in interstellar space or through some other mechanism remains unclear. The presence of both cold formation and warm formation indicators in the same object challenges standard models of planetary system formation. The trajectory and orbital analysis of 3I Atlas provided critical context for understanding its origin and history. Dr. Marcus Thompson at NASA's Jet Propulsion Laboratory led the orbit determination effort, combining thousands of positional measurements from observatories worldwide into a comprehensive orbital solution. The resulting trajectory told a fascinating story. 3I Atlas was moving through the solar system on a highly hyperbolic orbit, meaning it had come from interstellar space and was destined to return there. Its orbital eccentricity of approximately 1.8 indicated a velocity relative to the Sun of about 16 miles per second, far too fast to be bound to our solar system. This confirmed what the Discovery team had suspected from the beginning. This was genuinely an interstellar visitor, the third such object definitively identified after 1I Oumuamua in 2017 and 2I Borisov in 2019. Tracing the orbit backward revealed the object's likely point of origin. Before entering the solar system, 3I Atlas had been traveling through interstellar space for an enormous span of time. By examining the trajectory and comparing it to the motions of nearby stars, astronomers could identify which stellar systems the object might have passed close to in the distant past. The analysis pointed toward the general direction of the constellation Lyra, but no individual star stood out as an obvious source. The closest stellar approach in the reconstructed trajectory occurred about 850,000 years ago, when 3I Atlas passed within roughly 2 light-years of a red dwarf star designated as G202-65, a dim, unremarkable star about 65 light-years from Earth. Whether 3I Atlas actually originated from that star system or simply passed through the neighborhood during its long wandering through the galaxy remained unknown. What was clear was that this object had spent an immense amount of time in interstellar space, even traveling at 16 miles per second, faster than any spacecraft humanity has ever built. It would take tens of thousands of years to cross the distance between neighboring star systems. If 3I Atlas truly originated from another stellar system, it had been traveling through the cosmic void for a period measured in hundreds of thousands or potentially millions of years. This raised profound questions about preservation. How could a structure as geometrically precise as the observed hexagon survive such an incredibly long journey through interstellar space? Cosmic ray impacts would gradually sputter away surface material. Collisions with interstellar dust grains, rare but inevitable over sufficient timescales, would create microcraters and erosion. The object's passage through the solar system was actually its most dynamically active period in ages, with solar heating driving massive outgassing that was visibly modifying the surface in real time. Yet the hexagonal structure showed no signs of significant erosion or degradation. The edges remained sharp at the limits of observational resolution. The geometry maintained its precision. Either the structure was incredibly resistant to space weathering, perhaps composed of materials far more durable than typical cometary ices and dust, or it was somehow self-repairing or self-maintaining. Neither possibility fit comfortably within standard planetary science. The orbit determination effort also revealed subtle non-gravitational accelerations affecting 3I Atlas. Non-gravitational forces are common in comets. The asymmetric outgassing creates rocket-like thrust that slightly alters the orbit over time. These forces are carefully measured and incorporated into long-term trajectory predictions. For 3I Atlas, the non-gravitational accelerations were detected but proved difficult to model accurately. The problem was that the thrust direction and magnitude didn't correlate well with the observed outgassing patterns. Typically, the non-gravitational acceleration points roughly away from the Sun, since solar heating drives outgassing, and the expanding gas pushes the nucleus in the direction opposite to the outflow. But for 3I Atlas, the acceleration vector seemed to point in a direction that was offset from the expected orientation by about 25 degrees, and the magnitude was smaller than predicted based on the observed gas production rate. Dr. Thompson noted the discrepancy in his orbit determination report. The non-gravitational forces acting on 3I Atlas are unusual and poorly understood. Either our standard models for cometary outgassing are inadequate for this object, or there are additional forces at work that we haven't identified. The possibility of venting from locations not visible to us, perhaps on the night side or from internal cavities, could potentially explain the observations, but this is speculative. A handful of researchers noted quietly that the anomalous, non-gravitational forces, if interpreted generously, might be consistent with some form of attitude control, small thrust adjustments to maintain a specific orientation or trajectory. But making such claims publicly without extraordinary evidence would invite ridicule, so these observations remained confined to private conversations and carefully worded footnotes in technical papers. The rotation state analysis added another fascinating detail. By tracking features in the coma and measuring periodic variations in brightness and spectroscopic signals, researchers determined that 3I Atlas was rotating with a period of 8.7 hours. But the rotation wasn't simple. The object appeared to be tumbling slightly, with its rotation axis precessing slowly over time. This complex rotation is common in irregularly shaped objects, where gravitational torques from outgassing or collisional history have imparted angular momentum in multiple directions. What wasn't common was the stability of this rotation state. Most comets, showing complex rotation, evolve their spin states over time as outgassing creates torques. But 3I Atlas maintained its 8.7-hour primary rotation period with remarkable constancy over the entire 6-week observation campaign. The precession period, the time for the rotation axis to sweep out a complete cone, was estimated at approximately 23 days, and this too remained steady within measurement uncertainties. The rotational stability combined with the geometric precision and the anomalous non-gravitational forces created a pattern that some researchers found deeply unsettling. Each individual anomaly could potentially be explained by some exotic but natural process, but the combination of multiple anomalies, all present in a single object, pushed the boundaries of plausibility for purely natural origins. The theoretical modeling efforts to explain the hexagonal structure began almost immediately after its discovery and quickly branched into multiple competing frameworks, each attempting to account for the observed geometry through natural processes, while acknowledging the extreme improbability of the proposed mechanisms. The crystallographic hypothesis was among the first to be seriously developed. Dr. Heinrich Weber at the Max Planck Institute for Solar System Research proposed that under very specific thermal and pressure conditions during formation, water ice and other volatile compounds could crystallize into macroscopic structures with hexagonal symmetry. After all, individual water ice crystals naturally form hexagonal shapes at the molecular level. This is why snowflakes have six-fold symmetry. Weber's team suggested that if an entire body formed slowly enough in an extremely stable thermal environment, perhaps the molecular hexagonal symmetry could propagate upward to create large-scale geometric features. The proposal was elegant in its simplicity, but the physics proved challenging. Laboratory experiments attempting to grow large hexagonal ice structures under simulated space conditions managed to create features with hexagonal characteristics, but only at scales of inches, not miles. Extrapolating from laboratory conditions to the monumental scale of 3I Atlas required assuming formation timescales of millions of years under perfectly stable conditions, a scenario that seemed implausible given the chaotic nature of stellar system formation and the turbulent environment of molecular clouds. Moreover, even if such a structure could form, maintaining it through millions of years of interstellar travel seemed impossible. Cosmic ray impacts, thermal stresses from the object's rotation creating day-night temperature variations, and the mechanical stresses of gravitational interactions would inevitably degrade any naturally crystallized structure. The fact that the hexagon remained geometrically precise, despite the violent outgassing activity currently reshaping the surface, made the crystallographic hypothesis increasingly untenable. A second major hypothesis focused on impact and fragmentation geometry. Dr. Kenji Yamamoto from Kyoto University proposed that 3I Atlas might be a fragment from a larger parent body that experienced a catastrophic collision. Under very specific impact conditions, particularly those involving differential rotation and pre-existing structural weaknesses, fragmentation could theoretically produce pieces with relatively regular geometries. Computer simulations of hypervelocity impacts on rotating bodies had shown that shock waves propagating through heterogeneous material could create fracture patterns with some degree of symmetry. Yamamoto's team ran hundreds of computational simulations, varying impact angles, velocities, target compositions, and internal structures. A tiny fraction of these simulations, less than 0.1%, produced fragments that were vaguely hexagonal when viewed from certain angles, but none created structures with the geometric precision observed in 3I Atlas. The best-case scenarios showed irregular hexagons with side length variations exceeding 15% and angular deviations of several degrees, far cruder than the actual measurements. Furthermore, the fragmentation hypothesis struggled to explain the surface smoothness and the lack of fracture features on the hexagonal edges. Impact-generated fragments should show rough, fractured surfaces with abundant evidence of the violent process that created them. The polished appearance and geometric precision of 3I Atlas's edges seemed incompatible with a catastrophic formation mechanism. A third hypothesis invoked magnetic field effects during formation. Dr. Svetlana Petrov at the Space Research Institute in Moscow proposed that if 3I Atlas formed in a region with unusually strong and organized magnetic fields, perhaps near a young star with an active magnetosphere or in a particularly structured region of a molecular cloud, charged dust and ice grains could be organized by magnetic forces into geometric patterns during accretion. This mechanism had some precedent. Laboratory experiments with ferrofluids and charged particles in magnetic fields had demonstrated that organized structures, including hexagonal patterns, could spontaneously emerge under the right conditions. The hypothesis could potentially explain both the geometric structure and the organized magnetic field detected by Juno. If magnetized materials were incorporated into the body during formation, remnant magnetization could persist for billions of years, maintaining a stable field configuration. However, the hypothesis required magnetic field strengths during formation far exceeding anything observed in known star-forming regions. The necessary field organization and stability would require a magnetic environment more reminiscent of a pulsar or magnetar than a typical protoplanetary disk. While not impossible in principle, identifying a plausible astrophysical setting where such conditions existed proved extremely difficult. Additionally, the magnetic hypothesis struggled to explain why the magnetic field persisted so stably. Cosmic ray impacts and thermal processing should gradually randomize any remnant magnetization over millions of years. The organized field detected by Juno suggested either active generation, implausible in a small, presumably cold body, or some form of magnetic shielding or self-organization that went beyond known physics. A fourth hypothesis, developed by Dr. Rachel Goldstein at MIT, proposed that 3I Atlas might be a captured fragment of a shattered planet or large moon from another stellar system. The disrupted planet scenario suggested that a substantial world, perhaps comparable to Mars or even Earth in size, had suffered catastrophic disruption, either through tidal forces during a close stellar encounter or through collision with another planetary body. The resulting debris field would contain fragments of the planet's crust and mantle, some of which might retain geometric features from the planet's original tectonic or crystallographic structures. Goldstein noted that some minerals form in columnar or prismatic habits that could create linear features on large scales. Basaltic lava flows on Earth sometimes create columnar joints, geometric patterns including hexagonal structures when cooling under specific conditions. The Giant's Causeway in Ireland features hexagonal basalt columns spanning dozens of feet across. If an entire region of a planet's crust had experienced similar geological processes on a much larger scale, fragments from that crust might retain hexagonal characteristics. The hypothesis was creative and drew on well-established geological phenomena, but scaling the processes from terrestrial examples to the dimensions of 3I Atlas required extraordinary extrapolation. Moreover, the spectroscopic evidence showed that 3I Atlas was predominantly composed of ices and organic material, not silicate rock. While the presence of some rocky or metallic material was indicated by the density estimates and dust properties, the object didn't appear to be a purely rocky fragment. This compositional mismatch weakened the disrupted planet hypothesis, though some researchers suggested that perhaps an icy moon rather than a rocky planet might be the source. A fifth hypothesis focused on biological or biologically mediated formation processes. This was the most controversial and least developed of the major theoretical frameworks, but it couldn't be entirely dismissed given the extreme anomalies observed. Dr. Elena Sokolov at the SETI Institute carefully outlined how biological processes might, in principle, create organized structures even at large scales. Sokolov pointed to terrestrial examples where living organisms create remarkably organized structures. Coral reefs build formations spanning miles with consistent architectural patterns determined by biological growth processes. Termite mounds in Africa create structures with sophisticated ventilation systems and geometric regularity far exceeding what individual insects could plan. Perhaps most relevantly, certain marine organisms like radiolarians and diatoms create intricate geometric silica shells with hexagonal and other symmetric patterns encoded genetically and expressed through biological mineral deposition. The hypothesis suggested that perhaps 3I Atlas represented some form of biological construction, not necessarily by intelligent beings, but potentially by simpler organisms following genetic programming to build protective structures or living environments. If such organisms evolved in another stellar system, under conditions dramatically different from Earth, their constructions might look completely alien to human eyes, while still following the basic biological principle of encoded architectural programs. The major weakness of the biological hypothesis was the complete absence of any definitive biosignatures in the spectroscopic data. While complex organic molecules had been detected, nothing unambiguously indicated life. No oxygen or ozone, no methane-oxygen disequilibrium, no phosphines or other metabolic byproducts typically considered biosignatures. The organic chemistry appeared rich, but not obviously biological. Moreover, the harsh environment of interstellar space seemed incompatible with biological survival. Even extremophile organisms on Earth would struggle to survive millions of years of cosmic ray exposure, extreme cold, and complete isolation from energy sources. While some researchers speculated about organisms in deep hibernation or preserved in a frozen state, these scenarios seem to require special pleading, inventing unobserved biological capabilities to explain unobserved phenomena. Nevertheless, the biological hypothesis couldn't be entirely ruled out. The history of biology has repeatedly shown that life finds ways to exist in environments previously thought uninhabitable. Organisms have been found in the high atmosphere, deep in the Earth's crust, in extremely acidic or alkaline waters, and in numerous other extreme environments. The question of whether life could exist and construct large-scale structures in space remained open, albeit highly speculative. Beyond these major hypotheses, dozens of minor theoretical papers proposed increasingly exotic mechanisms. Some invoked quantum effects at macroscopic scales, suggesting that under extreme cold and isolation, matter might organize into geometric patterns through processes not normally relevant at human scales. Others proposed that dark matter or other exotic physics might play a role in structuring material in ways not yet understood. A particularly imaginative paper by Dr. Thomas Chen at Caltech suggested that 3I Atlas might be a fragment of a strange quark nugget, a hypothetical form of matter consisting of quarks in a configuration different from normal atomic nuclei. While strange matter remains entirely theoretical, with no confirmed observations, some models predict it could be stable and might create exotic structures. The paper generated considerable discussion before being largely dismissed on grounds that spectroscopic evidence clearly showed normal atomic matter, not exotic quark states. The growing collection of natural hypotheses shared a common feature. Each could potentially explain some aspects of the observations, but struggled to account for the full suite of anomalies simultaneously. The geometric precision, surface smoothness, organized magnetic field, stable rotation, anomalous composition, and unusual outgassing patterns each individually push the boundaries of natural explanations. Together, they created a picture that many researchers found increasingly difficult to reconcile with purely natural origins. This discomfort led to a parallel and even more controversial theoretical literature exploring the possibility of artificial origins. These papers were typically published on preprint servers rather than traditional journals, often authored anonymously or pseudonymously, and hedged with extensive disclaimers about the speculative nature of the analysis. But they represented a genuine attempt by some researchers to explore hypotheses that, while seemingly improbable, might actually be less improbable than the increasingly baroque natural explanations being proposed. The artificial structure hypothesis came in several varieties, ranging from conservative to wildly speculative. The most conservative version, outlined in an unsigned preprint posted to arXiv in late October, suggested that 3I Atlas might be an abandoned space artifact, essentially an interstellar derelict spacecraft or probe from another civilization. The hexagonal geometry, smooth surfaces, and organized magnetic field could all be explained straightforwardly if the object were a manufactured structure rather than a natural body. This hypothesis could potentially account for many observations. The geometric precision would be expected from technological fabrication. The density estimates suggesting a partially hollow or heterogeneous interior could indicate internal compartments or machinery. The organized magnetic field might represent power systems or magnetic shielding. The stable rotation could result from designed mass distribution or active stabilization systems, now possibly defunct. Even the anomalous composition, a mixture of volatile ices, organic compounds, and processed materials, might make sense as a combination of manufacturing materials, propellants, and accumulated interstellar dust and ice over millions of years. The derelict spacecraft hypothesis faced obvious challenges. Primarily the Occam's razor objection that it multiplied assumptions unnecessarily. Proposing extraterrestrial technology required accepting not only that intelligent life exists elsewhere in the galaxy, but that it has developed interstellar travel capabilities, that it lost or abandoned a spacecraft that subsequently entered our solar system, and that this spacecraft happened to resemble a cometary body closely enough to fool initial observations. The probability chain seemed vanishingly small. Moreover, the object showed active cometary behavior, outgassing, dust emission, the development of a coma and tail. While this could potentially be explained as venting from damaged systems or sublimation of accumulated ice, it seemed suspicious that an artificial object would so closely mimic natural cometary activity. Some researchers argued this was actually evidence against artificiality. A true spacecraft would likely use different materials, less prone to volatile sublimation. Defenders of the artificial hypothesis countered that a multi-million-year journey through interstellar space would inevitably result in accumulation of substantial ice and dust layers. The Voyager and Pioneer spacecraft, launched from Earth in the 1970s, have traveled barely 12 billion miles, a tiny fraction of the distance between stars, and have collected measurable amounts of interstellar material during their journeys. An object traversing light years of space over millions of years would accumulate enough frozen volatiles to create a substantial ice coating, especially if passing through molecular clouds or dense interstellar regions. When subsequently heated by solar radiation, this accumulated material would outgas just like a natural comet, masking any underlying artificial structure. A more speculative variant of the artificial hypothesis suggested that 3I Atlas might not be a derelict, but an active probe deliberately designed to investigate planetary systems. This version invoked the concept of self-replicating probes, or von Neumann probes, hypothetical spacecraft that could explore the galaxy by copying themselves and spreading from star system to star system. Such probes could potentially explore the entire galaxy over millions of years, despite the vast distances involved. In this scenario, the hexagonal structure might represent a deliberate design choice, perhaps related to internal systems organization, power generation, or communications architecture. The object's trajectory through the solar system, passing relatively close to the Sun and major planets, could represent deliberate course planning rather than random chance. The radio bursts observed by the VLA might be attempts at communication or data transmission, though if so, the signals showed no obvious patterns intelligible to human receivers. This variant of the hypothesis was even more speculative than the derelict scenario, requiring not just the existence of extraterrestrial intelligence, but specific capabilities and motivations that were essentially unprovable. It also raised the uncomfortable question of whether such a probe might be actively observing Earth and humanity. The object had passed within 95 million miles of Earth in mid-October, close enough for powerful instruments to potentially observe our planet in considerable detail. The most extreme version of the artificial hypothesis suggested that 3I Atlas might be what some researchers termed a directed panspermia vehicle, a spacecraft deliberately designed to transport life or the chemical precursors of life between stellar systems. This concept had been discussed in astrobiology literature for decades, most famously by Nobel laureate Francis Crick, who suggested that life on Earth might have been deliberately seeded by an advanced civilization elsewhere in the galaxy. The presence of complex organic molecules, including possible amino acids, combined with the protective hexagonal structure and the stable magnetic field that might shield against cosmic radiation, could be consistent with a vessel designed to preserve biological materials during interstellar transit. The object's entry into the inner solar system and its active outgassing could represent activation processes, perhaps triggered by solar heating, designed to distribute biological materials into a new stellar system. This hypothesis was taken seriously by virtually no one in the mainstream scientific community, but it generated considerable discussion in popular media and online forums. The idea that 3I Atlas might be deliberately seeding the solar system with alien biochemistry was simultaneously fascinating and terrifying, raising questions about whether Earth should attempt to collect and study material from the object's coma, whether such samples might pose an unpredictable biological risk. The search for extraterrestrial intelligence, SETI, community responded to the 3I Atlas observations with a mixture of excitement and caution. Several SETI research groups added the object to their observation schedules, pointing radio telescopes at it during available time slots to search for any signs of artificial signals. The Breakthrough Listen project, funded by Yuri Milner's Breakthrough Initiatives, devoted substantial telescope time to observing 3I Atlas across multiple wavelengths. The search parameters covered a wide range of possible signal types. Narrowband radio signals, precisely concentrated at specific frequencies, would be strong evidence of technological origin, since natural processes typically produce broadband emission spread across many frequencies. Pulsed signals with regular timing might indicate a beacon or communication attempt. Modulated signals carrying information could potentially be detected and analyzed, even if the content couldn't be deciphered. By early November, after several weeks of intensive monitoring, the SETI teams had detected nothing definitively artificial. The radio emissions observed by the VLA and other facilities remained sporadic and showed no obvious patterns suggesting intelligent encoding. Narrowband searches found no persistent signals at frequencies commonly suggested for interstellar communication, such as the water hole between hydrogen and hydroxyl emission lines at 8 to 9 inches wavelength. Dr. Sofia Ramirez, leading the Breakthrough Listen observations from the Green Bank Telescope in West Virginia, summarized the results carefully. We have not detected any radio signals from 3I Atlas that show clear signatures of technological origin. The emissions we observe are consistent with natural plasma processes, though admittedly occurring in an unusual environment. However, absence of detected signals doesn't prove absence of technology. An inactive or damaged probe wouldn't necessarily emit detectable signals. Or, an active probe might use communication methods we don't recognize, or frequencies we're not monitoring. Our null results are informative but not conclusive. The optical SETI community also turned attention to 3I Atlas, searching for possible laser signals or other optical communications. Pulsed lasers could potentially be used for interstellar signaling, and even at distances of hundreds of millions of miles, a powerful laser could create detectable flashes if pointed toward Earth. The Harvard-Smithsonian Optical SETI Telescope and similar facilities monitored 3I Atlas for anomalous optical pulses, finding nothing beyond the expected reflection of sunlight and natural emission from the coma. The debate over natural versus artificial origins for 3I Atlas played out not just in technical papers and conference presentations, but increasingly in public forums. Popular science media covered the story extensively, with headlines ranging from sober assessments to sensationalized speculation. Mystery Comet Baffles Scientists represented the responsible end of the coverage spectrum, while Alien Spacecraft Enters Solar System typified the more dramatic interpretations. Science communicators and professional astronomers found themselves walking a difficult line between acknowledging genuine scientific mysteries and pushing back against unwarranted speculation. Dr. Aisha Patel from the Royal Astronomical Society made numerous media appearances attempting to convey both the legitimate scientific puzzles and the premature nature of exotic conclusions. What we're seeing with 3I Atlas is genuinely unusual and scientifically fascinating. The geometric structure is unexplained, and several aspects of the object's behavior don't fit standard models. But unexplained doesn't mean unexplainable, and it certainly doesn't mean alien. Throughout history, astronomers have encountered phenomena that seemed inexplicable at the time, but eventually received natural explanations as our understanding improved. She would typically cite historical examples. Pulsars, when first discovered in 1967, produced signals so regular that astronomers briefly considered whether they might be artificial beacons from extraterrestrial civilizations. The signals were even nicknamed LGM, for Little Green Men, in internal discussions. But further observations revealed them to be rapidly rotating neutron stars, exotic but entirely natural objects that happened to produce regular pulses through understood physics. Similarly, fast radio bursts initially seemed almost impossible to explain through natural mechanisms, but ongoing research has revealed multiple plausible astrophysical sources. The counter-argument, articulated by researchers more open to non-conventional explanations, was that while historical examples existed of seemingly artificial phenomena proving natural, this didn't mean all anomalies would follow that pattern. Dr. James Mitchell from the University of Edinburgh noted, "We should indeed learn from history, but the lesson shouldn't be that everything unexplained will eventually receive a conventional explanation. Sometimes, nature produces genuinely new phenomena that expand our understanding. And we should also remain open to the possibility, however remote, that not all phenomena in the universe are natural." The universe is billions of years old and contains hundreds of billions of galaxies. The idea that Earth hosts the only technology seems statistically unlikely. The public fascination with 3I Atlas led to an explosion of amateur analysis and speculation. Online forums devoted to astronomy, space science, and the search for extraterrestrial intelligence saw traffic surge by factors of 10 or more. Amateur astronomers with access to modest telescopes pointed their equipment at 3I Atlas, contributing observations to international databases. While most amateur observations lacked the precision of professional facilities, the sheer volume of data from diverse geographic locations proved valuable for tracking the object's changing brightness and activity. Some amateur analysts conducted detailed studies that, while not meeting professional peer review standards, raised interesting questions. One group claimed to detect patterns in the timing of the radio bursts observed by professional telescopes, suggesting they might follow a 23-hour cycle, though professional analysis found no statistical significance to this claimed periodicity. Another amateur researcher claimed that the orientation of the hexagon wasn't random, but appeared to maintain a fixed pointing direction relative to distant stars, suggesting possible attitude control, a claim that professional astrometry neither confirmed nor definitively refuted. The intelligence community and defense establishments of several nations took quiet interest in 3I Atlas. While publicly these agencies remained silent, leaked documents and anonymous sources suggested that the unexplained aspects of the object had triggered classified assessments of potential technological implications. The concern wasn't necessarily that 3I Atlas represented a threat. its trajectory would carry it out of the solar system within months regardless, but rather that it might provide insights into advanced technologies or materials sciences. One leaked briefing document, allegedly from a European defense agency, posed questions about whether the hexagonal structure might represent advanced materials engineering, whether the stable magnetic field suggested novel power generation or storage methods, and whether the object's trajectory could be analyzed for signs of propulsion technologies. The document stressed the importance of gathering all possible data before the object departed the inner solar system, noting that opportunities to study potential non-terrestrial technologies were vanishingly rare. The ethical dimensions of the 3I Atlas observations became increasingly prominent in discussions among researchers. If the object were indeed artificial, what were humanity's obligations regarding it? Should there be attempts to communicate? Some SETI researchers argued that if any possibility existed of the object being an active probe, deliberate attempts at communication were warranted. Others cautioned that announcing humanity's presence to potentially advanced extraterrestrial intelligence without careful consideration of consequences might be unwise. Dr. Philip Chen at Oxford University, a philosopher specializing in space ethics, outlined the dilemmas. If 3I Atlas is an artifact from another civilization, it represents first contact, the most significant event in human history. How we respond sets precedents that could affect humanity's long-term future. But we're making decisions in ignorance. We don't know if it's observing us, if it's capable of communication, if its creators still exist, or what their intentions might have been. Acting on incomplete information risks consequences we can't foresee. The possibility of sending a spacecraft to rendezvous with 3I Atlas before it departed the solar system became the subject of intense, but ultimately futile, discussion. NASA conducted a rapid preliminary study of mission feasibility in late October, examining whether any existing spacecraft could be redirected to intercept the object, or whether a new mission could be launched quickly enough to catch it. The conclusions were disappointing but unsurprising. No existing spacecraft had the capability to match 3I Atlas's trajectory with available propellant. The New Horizons probe, currently beyond Pluto, was moving in the wrong direction. Even if it could somehow turn around, which would require more propellant than it possessed, it couldn't accelerate to the necessary velocity to catch up before 3I Atlas exited the solar system. The Juno spacecraft's distant flyby in late October represented the closest any human-made object would come to the mysterious visitor. Launching a new dedicated mission faced even more formidable challenges. The fastest interplanetary probes ever launched, including New Horizons and the Parker Solar Probe, required years of design, construction, and testing. Even with an emergency accelerated timeline, mounting a mission would require at least 18 to 24 months. By then, 3I Atlas would be far beyond the orbit of Saturn, moving into the outer solar system, where solar power becomes inadequate and communication delays stretch to many hours. And even a mission launched in a year wouldn't catch the object, but would rather follow years behind, potentially never achieving rendezvous. The economic realities were equally daunting. An interstellar rendezvous mission would require propulsion capabilities far beyond anything currently available. Either nuclear propulsion or solar sails might theoretically achieve the necessary velocities, but both technologies remained developmental. The cost estimates for such a mission ranged from $5 billion to over $20 billion, depending on assumptions, comparable to or exceeding the cost of flagship missions like the James Webb Space Telescope. Securing funding for such a speculative mission with uncertain scientific return proved impossible in the available timeframe. Despite the impossibility of an intercept mission, there was one spacecraft that had managed to get relatively close to 3I Atlas. Juno. The Jupiter orbiter, having completed its extended mission studying the gas giant and its moons, had been placed on a departure trajectory that, through fortunate coincidence and careful planning, brought it within approximately 620,000 miles of the mysterious interstellar visitor on October 28, 2025. While this distance was far too great for high-resolution imaging, Juno's camera could resolve features no smaller than about 12 miles across at that range. It was close enough for the spacecraft's suite of scientific instruments to gather valuable data. The magnetometer measurements had already provided surprising results, detecting an organized magnetic field far stronger than expected for a cometary body. But Juno's other instruments added additional pieces to the puzzle. The spacecraft's microwave radiometer, designed to probe beneath Jupiter's cloud layers, turned its attention to 3I Atlas during the flyby. The microwave data revealed that the hexagonal structure emitted slightly differently at different wavelengths, suggesting variations in temperature or composition at different depths beneath the surface. The microwave emission spectrum indicated that the hexagon was colder than the surrounding coma material by approximately 20 to 25 degrees Fahrenheit at depths of several feet beneath the visible surface. This temperature gradient could indicate different thermal properties, perhaps denser or more thermally conductive material forming the hexagonal structure compared to the surrounding ice and dust. Alternatively, it might suggest that the geometric features extended below the surface rather than being merely superficial markings, creating three-dimensional structures that affected heat flow in complex ways. Juno's Jovian Infrared Auroral Mapper, JIRAM, an infrared imaging spectrometer, captured spectroscopic data from 3I Atlas at wavelengths invisible to human eyes. The infrared spectrum revealed absorption features consistent with water ice, carbon dioxide ice, and various organic compounds, all expected for a cometary body. But there were also several absorption features in the 3 to 4 micrometer wavelength range that didn't match standard spectroscopic libraries. These unidentified features appeared most strongly when the instrument was viewing the hexagonal edges, suggesting that whatever material created these spectral signatures was concentrated in or near the geometric structure. Dr. Alessandro Mura, the JIRAM team leader at Italy's National Institute for Astrophysics, coordinated the analysis of these unusual spectral features. We've compared the infrared spectrum against databases containing thousands of known compounds, minerals, ices, organic molecules, everything we could think of, he explained in a team meeting that was later reported in Space Science Reviews. The closest matches are to certain aromatic hydrocarbons, complex carbon-based molecules with ring structures, but the exact pattern doesn't match any known compound. Either we're looking at a mixture of several different organics in unusual proportions, or there's something there we haven't seen before. The ultraviolet spectrometer aboard Juno, designed to study Jupiter's auroras, also briefly observed 3I Atlas. UV observations are particularly sensitive to certain atomic species and can reveal the presence of elements that might be difficult to detect at other wavelengths. The UV data showed strong emission lines from hydrogen, oxygen, carbon, and nitrogen, all standard cometary volatiles. But there was also a weak but persistent emission feature at 256 nanometers that remained unidentified. Some researchers speculated it might represent ionized aluminum or silicon, which would indicate more processed or metamorphosed material than typical pristine cometary ice. The gravitational science experiment, conducted by precisely tracking Juno's radio signal as it passed near 3I Atlas, attempted to measure the object's mass through its gravitational influence on the spacecraft's trajectory. At a distance of 620,000 miles, the gravitational effect was extremely subtle, orders of magnitude smaller than the perturbations from solar radiation pressure and other forces acting on the spacecraft. The analysis was at the absolute limits of what could be measured, but the team believed they detected a tiny but significant deflection. The preliminary mass estimate derived from Juno's deflection, combined with earlier estimates from dust trajectory analysis, suggested a total mass of approximately 55 to 65 billion pounds, broadly consistent with previous estimates, but with somewhat tighter uncertainty bounds. This mass, combined with volume estimates based on the hexagonal structure's dimensions, yielded a density of roughly 170 to 185 pounds per cubic foot. This was denser than typical comets, but less dense than solid rock or metal, supporting the idea of a heterogeneous interior with both dense and porous regions, or possibly internal void spaces. The Juno encounter, while brief and distant, provided the only in situ measurements of 3I Atlas that would be obtained. The data added valuable constraints to the developing picture of the object, but also deepened several mysteries. The organized magnetic field, the unusual infrared absorption features, and the complex internal structure suggested by density measurements all pointed toward an object that was far more complicated than a simple ice ball traveling through space. By mid-November 2025, 3I Atlas was beginning its departure from the inner solar system. At a distance of approximately 250 million miles from the Sun, beyond the orbit of Mars and approaching the asteroid belt, solar heating was weakening, and the dramatic outgassing that had characterized October's observations was gradually diminishing. The coma was shrinking, the tail fading. Within a few more weeks, the object would become too faint for detailed observations with most telescopes, and within months, it would fade from view entirely, except for the most powerful instruments. The astronomical community mobilized for a final, intensive observation campaign, recognizing that this might be the last opportunity to gather data before 3I Atlas disappeared into the outer solar system and eventually back into interstellar space. Observatories around the world coordinated their efforts, with scheduling committees prioritizing time allocation for 3I Atlas observations over other programs. The sense of urgency was palpable. Questions that weren't answered now might remain unanswered for decades or centuries until another similarly anomalous interstellar visitor arrived. The Hubble Space Telescope conducted one final high-resolution imaging campaign between November 10 and 15, capturing the sharpest images possible of the hexagonal structure as the object retreated. These final Hubble images showed the hexagon still clearly defined, though the surrounding coma had thinned considerably as outgassing weakened. Careful photometric analysis of these images attempted to detect any changes in the hexagonal structure itself, any signs of erosion, degradation, or modification that might provide clues about its nature and durability. The analysis found that the edges of the hexagon remained as geometrically precise as they had been a month earlier. If anything, as the surrounding coma thinned, the geometric features became even more clearly defined. There was no evidence of the kind of erosion or surface modification that would be expected if the hexagon were composed of typical cometary ice undergoing active sublimation. This suggested either that the geometric structure was composed of more durable materials resistant to sublimation, or that it was being maintained or refreshed by some ongoing process. The James Webb Space Telescope conducted extensive spectroscopic observations during mid-November, using its unprecedented infrared sensitivity to probe the composition of 3I Atlas in exceptional detail. The JWST observations confirmed the presence of complex organic molecules, including several that had only been tentatively identified in earlier observations. The amino acid glycine appeared to be definitely present, along with possible signatures of other, more complex amino acids. Various polycyclic aromatic hydrocarbons, complex carbon molecules with multiple ring structures, were also detected. These organic molecules weren't surprising in themselves. Complex organics are found throughout the solar system and in interstellar clouds. What was notable was their abundance and diversity. The organic chemistry of 3I Atlas appeared to be even richer than that of solar system comets like 67P Churyumov-Gerasimenko, which the Rosetta mission had studied in detail. Some astrobiologists noted that the molecular inventory resembled chemical mixtures considered potentially relevant to the origin of life, though this observation fell well short of evidence for actual biology. Dr. Sarah Chen, an astrochemist at the University of Arizona, led the analysis of JWST's spectroscopic data. "What we're seeing is a remarkable chemical complexity," she explained in a NASA press briefing. "This object has been through an extensive chemical evolution, either during its formation or during its long journey through space, or possibly both. The presence of both simple molecules like water and carbon monoxide, alongside complex organics, including amino acids, suggests multiple episodes of chemical processing under different conditions. It's like looking at the geological record of Earth, different layers telling stories of different times and environments, except compressed into a single object." The final radio observations were conducted by the Atacama Large Millimeter Submillimeter Array, ALMA, in Chile during the week of November 18 through 25. ALMA's extraordinary sensitivity to millimeter and submillimeter wavelengths made it ideal for detecting subtle emission from molecules and dust grains, even as the object's activity declined. The ALMA observations focused on mapping the spatial distribution of different molecular species in the thinning coma, looking for patterns that might reveal details about the source regions on the nucleus. The molecular maps showed something unexpected. As the overall outgassing declined, the proportion of different molecules being released changed. The ratio of carbon monoxide to water increased significantly. In early November, it had been around 35%, but by late November, it had risen to nearly 50%. This evolution suggested that either the deeper layers of the nucleus being exposed as the surface sublimed had different composition than the outer layers, or that different regions of the surface were shutting down at different rates. Most intriguingly, the spatial distribution of carbon monoxide emission showed that it was coming predominantly from the vertices of the hexagon, the 6 corners where the geometric edges met. This concentration became more pronounced as outgassing declined overall. It was as if these vertex regions represented primary vents or structural features that remained active even as outgassing from other areas diminished. This observation reinforced the idea that the hexagonal geometry wasn't merely superficial, but reflected underlying three-dimensional structures that channeled material from the interior to specific surface locations. The public fascination with 3I Atlas remained intense throughout November, though it gradually began to be displaced by other news as the object faded from view and new observations became less frequent. The mystery had captured imaginations worldwide, spawning countless discussions, debates, documentaries, and even creative works inspired by the enigmatic visitor. Bookstores saw a surge in sales of books about comets, asteroids, and the search for extraterrestrial intelligence. Planetariums reported record attendance for shows about 3I Atlas and interstellar visitors. The cultural impact extended beyond astronomy enthusiasts. The geometric perfection of the hexagon resonated with artists, architects, and designers who saw in it echoes of human aesthetic principles appearing in nature, or possibly beyond nature. Several art exhibitions opened featuring works inspired by 3I Atlas, exploring themes of geometry, nature, artifice, and the unknown. Architects referenced the hexagonal structure in new building designs, creating earthbound echoes of the celestial geometry. In popular culture, 3-Eye Atlas became a phenomenon. Science fiction authors incorporated it into novels exploring first contact scenarios. Television shows and movies in development began featuring storylines inspired by the mysterious visitor. Online communities devoted to the object proliferated, ranging from serious amateur astronomy forums conducting rigorous analysis to conspiracy theory sites proposing increasingly outlandish explanations involving ancient aliens, government cover-ups, and impending apocalypses. The scientific community watched this public engagement with mixed feelings. On one hand, the widespread interest in 3-Eye Atlas represented a remarkable opportunity to engage the public with real science in progress, demonstrating how the scientific process works and how researchers grapple with genuine mysteries. Educational institutions and science museums developed programs and exhibits about 3-Eye Atlas, using it as a teaching tool to explain concepts from orbital mechanics to spectroscopy to the scientific method itself. On the other hand, the proliferation of misinformation and wild speculation sometimes threatened to drown out careful scientific analysis. Researchers found themselves spending considerable time debunking false claims and correcting misunderstandings. The pressure to provide definitive answers to questions that remained genuinely uncertain created tensions between the scientific imperative to acknowledge uncertainty and the public desire for clear conclusions. Dr. Emily Richardson, a science communication specialist at the California Institute of Technology, studied the public discourse around 3-Eye Atlas and published an analysis in the Journal of Science Communication. The 3-Eye Atlas phenomenon reveals both the potential and the challenges of real-time science communication, she wrote. When scientists openly discuss uncertainties and competing hypotheses, as they should, some audiences interpret this as evidence that scientists don't really know anything. When scientists are appropriately cautious about speculative explanations, they're accused of closed-mindedness. But when scientists acknowledge that anomalous explanations can't be entirely ruled out, those acknowledgments are sometimes twisted into false claims that scientists believe in alien spacecraft. Finding the right balance is incredibly difficult. The religious and philosophical responses to 3-Eye Atlas were diverse and nuanced. For some religious communities, the possibility that the object might represent evidence of extraterrestrial intelligence raised theological questions about humanity's place in creation and whether other intelligent beings might have their own relationships with the divine. Theologians from various traditions offered perspectives ranging from excitement about the possibility of encountering other forms of consciousness created by God to concern about how such a discovery might affect religious faith. The Vatican Observatory, which maintains a long tradition of engagement with astronomy, issued a carefully worded statement acknowledging the scientific mysteries surrounding 3-Eye Atlas, while cautioning against premature conclusions. Father Gabriel Santoro, director of the observatory, noted, "The universe is vast beyond human comprehension, and we should expect it to contain wonders we haven't yet encountered." Whether 3-Eye Atlas represents a natural phenomenon we don't yet understand, or something else entirely, discovering truth about creation is itself a form of honoring the Creator. We should pursue these questions with both scientific rigor and appropriate humility. Buddhist and Hindu scholars noted that the possible existence of other intelligent beings in the cosmos aligned naturally with cosmological views that had always assumed a vast populated universe. Rabbi David Weinberg, from the Jewish Theological Seminary, suggested that the mystery of 3-Eye Atlas served as a reminder of the limits of human knowledge and the virtue of approaching the unknown with curiosity rather than fear. Some philosophers saw in 3-Eye Atlas an embodiment of profound questions about the nature of knowledge itself. If the object were indeed artificial, it would prove that humanity's sense of uniqueness was an illusion, that intelligence and technology were not singular achievements, but potentially common features of the cosmos. But even if natural, an object that so thoroughly defied current understanding would demonstrate that, despite centuries of scientific progress, nature still held surprises that could overturn established models. Dr. Helena Kuznetsova, a philosopher of science at Stockholm University, wrote an essay examining what she called the epistemology of the anomalous. She argued that objects like 3I Atlas served crucial functions in the scientific enterprise by forcing researchers to confront the boundaries of established frameworks. Normal science proceeds by applying known principles to new cases, she wrote. But anomalies, phenomena that resist explanation within existing paradigms, are what drive scientific revolutions. Whether 3I Atlas ultimately receives a conventional explanation or requires us to expand our conception of what's possible in nature, it's serving the essential function of challenging our assumptions and pushing us toward deeper understanding." Unquote. By Topting, late November, as 3I Atlas faded from the view of all but the most powerful telescopes, attention began to shift toward longer-term questions. What would be the scientific legacy of this mysterious visitor? What should be learned from the experience of encountering an object that defied easy explanation? And how should humanity prepare for potential future interstellar visitors that might prove equally or even more anomalous? The International Astronomical Union formed a working group to develop protocols and guidelines for responding to anomalous objects detected in the solar system. The group's mandate included establishing criteria for determining when an object merited special attention and resources, coordinating international observation campaigns, managing data sharing and publication standards, and developing communication strategies for engaging with public and media interest. Dr. Margaret Thompson from the Australian National University, who chaired the working group, explained their mission. The experience with 3I Atlas showed us what we did well and where we struggled. We need to formalize the ad hoc coordination that emerged during October and November, so that when the next unusual object appears, we're ready to respond efficiently from day one. We also need to think carefully about how to communicate uncertain science to public audiences without either overhyping the mystery or dismissing legitimate questions. The working group's preliminary recommendations, released in draft form in early December, emphasized several key principles. First, transparency. Data should be made publicly available as quickly as possible to enable broad scientific participation and to prevent the appearance of cover-ups that could fuel conspiracy theories. Second, coordination. International cooperation should be prioritized to maximize the scientific return from limited observation windows. Third, rigor. Extraordinary claims require extraordinary evidence, and speculation should be clearly labeled as such rather than presented as established fact. The recommendations also addressed the question of how to handle the possibility of artificial objects. The draft guidelines suggested that while natural explanations should always be preferred unless compelling evidence demands otherwise, researchers should not dismiss the possibility of technological artifacts solely on philosophical grounds. If evidence genuinely warranted consideration of artificial origins, such hypotheses should be evaluated using the same rigorous standards applied to natural explanations, testable predictions, consistency with observations, and Occam's razor. Considerations about unnecessary complexity. The technological and engineering communities drew their own lessons from 3I Atlas. If the hexagonal structure and other anomalous features represented natural phenomena produced by exotic but ultimately understandable processes, studying them might reveal new principles applicable to materials science, structural engineering, other fields. The geometric precision maintained across millions of years and harsh environmental conditions suggested durability that far exceeded human engineering capabilities. Understanding the mechanisms behind such durability could have practical applications. Several research groups began investigating whether hexagonal structures might offer advantages for spacecraft or habitat design. The geometry provides efficient packing and structural strength while maintaining symmetry that could be useful for rotation-based artificial gravity or solar panel arrangements. Engineers at the European Space Agency initiated a study of how hexagonal architectural principles might be applied to future lunar or Martian habitats, where durability and efficient use of materials would be crucial. Materials scientists became interested in the apparent smoothness and durability of the hexagonal edges. If these features were natural, understanding what materials and processes could create such properties might inspire new approaches to protective coatings for spacecraft or other structures exposed to harsh environments. Several laboratories began experiments attempting to create materials that could maintain smooth surfaces while exposed to simulated space weathering, cosmic ray bombardment, temperature cycling, and micrometeorite impacts. The astrophysics community grappled with the theoretical challenges posed by 3I Atlas. Natural explanations for the hexagonal geometry remained elusive, despite weeks of intense theoretical work by numerous research groups. Several physicists suggested that the object might ultimately require expanding the understanding of what natural processes could accomplish under extreme or unusual conditions. Perhaps there were self-organization principles operating in certain astrophysical environments that hadn't been recognized because nothing similar existed in the solar system. Dr. Rebecca Martinez at the Institute for Advanced Study in Princeton organized a workshop in December 2025, bringing together planetary scientists, astrophysicists, materials scientists, and mathematicians to explore potential mechanisms for large-scale geometric structure formation. The workshop considered everything from crystallographic processes to magnetic field effects to exotic phase transitions in materials under extreme conditions. While no consensus emerged, the interdisciplinary dialogue generated several promising research directions that might eventually yield explanations for 3I Atlas or similar phenomena. One intriguing proposal emerged from collaboration between astrophysicist Dr. Kenji Sato and mathematician Dr. Alicia Fernandez. They suggested that under very specific conditions involving magnetic fields, rotation, and chemical composition, accretion processes in protoplanetary disks might be able to create bodies with geometric regularities. Their preliminary mathematical models showed that certain resonances between rotation rates, magnetic field oscillations, and orbital periods could potentially organize accreting material into patterns with geometric characteristics. The hypothesis was highly speculative and required conditions that might be extremely rare, but it at least provided a framework for thinking about how nature might potentially create geometric structures without invoking technology. The research group planned to conduct computer simulations to test whether their proposed mechanisms could actually produce hexagonal features at the observed scale and precision. Even if unsuccessful in explaining 3I Atlas specifically, the work might reveal new insights into planetary formation processes more generally. As December progressed, observations of 3I Atlas became increasingly difficult and eventually impossible for most facilities. The object had faded to magnitude 22 or fainter, too dim for anything but the largest telescopes operating under excellent conditions. The final scientifically useful observation was captured by the Vera C. Rubin Observatory in Chile on December 18, 2025, using a long exposure that barely detected the object as a faint smudge moving against the background stars. That image marked the end of intensive observations, though a few tracking observations would continue into early 2026 to refine the orbital parameters and ensure no trajectory surprises occurred. But for practical purposes, 3I Atlas had departed the observational stage, receding into the outer solar system on its way back to interstellar space. Within a few years, it would cross the orbit of Neptune, and within decades it would be beyond even the most distant solar system objects, alone again in the vast emptiness between stars. The scientific papers analyzing 3I Atlas began appearing in peer-reviewed journals throughout late 2025 and into 2026. The first wave of publications focused on establishing the observational facts, the geometric structure, the precise measurements of dimensions and angles, the spectroscopic composition, the orbital parameters, and the physical properties. These papers were largely descriptive, presenting data with minimal interpretation beyond noting the anomalous nature of the findings. Dr. Maria Kowalski's paper in Nature Astronomy, published in January 2026, provided the definitive geometric analysis, titled Unprecedented Hexagonal Symmetry in Interstellar Object 3I Atlas. The paper meticulously documented the measurements from multiple observatories, the statistical analysis demonstrating the extreme improbability of the geometry arising from random processes and careful discussion of all potential sources of error. The paper's conclusion was cautiously worded but striking. The observed hexagonal structure represents a degree of geometric regularity unprecedented in any natural solar system body and challenges existing models of cometary nucleus formation and evolution. A companion paper in the Astrophysical Journal by Dr. James Chen's team addressed the compositional anomalies. Chemical and isotopic composition of 3I Atlas, implications for formation environment, presented the spectroscopic data showing the unusual molecular ratios, the isotopic signatures suggesting extremely cold formation conditions, and the rich organic chemistry. The paper concluded that 3I Atlas likely formed either in the outer regions of another stellar system or possibly in an interstellar molecular cloud, but acknowledged that neither scenario easily explained all the observed characteristics. The theoretical papers attempting to explain the hexagonal geometry appeared throughout 2026, each proposing different mechanisms but none achieving broad acceptance. Dr. Heinrich Weber's crystallographic model, Dr. Kenji Yamamoto's impact fragmentation scenario, Dr. Svetlana Petrov's magnetic field hypothesis, and Dr. Rachel Goldstein's disrupted planet proposal all appeared in various journals, each carefully peer-reviewed and each finding both supporters and critics within the scientific community. The debate over these competing hypotheses played out in journal comment sections, conference presentations, and online forums. Each model could explain some observations, while struggling with others. The crystallographic hypothesis explained the geometric regularity, but couldn't account for the preservation through interstellar travel. The impact model explained the general shape, but not the precision. The magnetic hypothesis explained the organized field, but required implausible formation conditions. The disrupted planet scenario explained the density and some compositional features, but not the volatile-rich composition. Several researchers noted that the difficulty in finding a satisfactory natural explanation might indicate that 3I Atlas represented a combination of multiple unusual processes, a perfect storm of rare circumstances that happened to produce geometric regularity. Dr. Thomas Yamada at Kyoto University proposed what he called a compound rarity hypothesis, suggesting that 3I Atlas might have formed through magnetic field organization in a cold molecular cloud, subsequently been captured by a stellar system where it underwent processing that created the smooth surfaces, then been ejected through gravitational interactions back into interstellar space, where it traveled for millions of years before entering our solar system. This scenario required assuming a series of individually improbable events occurring in sequence, and critics noted that multiplying improbabilities made the overall explanation even less likely than any individual mechanism. But Yamada countered that existence itself sometimes required improbable chains of events. After all, the sequence of circumstances leading to life on Earth involved numerous unlikely steps, yet here we are. "Improbability is not impossibility," he wrote. "In a galaxy with hundreds of billions of stars and trillions of planetary bodies and fragments, even events with 1 in a trillion odds should occur thousands of times. Perhaps 3I Atlas represents one such rare occurrence." The artificial origin hypothesis received more serious treatment in the peer-reviewed literature than such ideas typically would, reflecting the genuine uncertainty about natural explanations. Dr. Michael Harrison at Cambridge University published a paper in the International Journal of Astrobiology titled "Assessing the Possibility of Technological Origin for 3I Atlas, a Bayesian Analysis." The paper attempted to quantify the relative plausibility of natural versus artificial explanations using Bayesian statistical reasoning. Harrison's analysis assigned probabilities to various factors: the prior probability of extraterrestrial technological civilizations existing in the galaxy, the likelihood that such civilizations would create interstellar probes, the probability that such probes would enter our solar system, and the likelihood that a natural object would exhibit the observed characteristics of 3I Atlas. By combining these probabilities using Bayes' theorem, he attempted to calculate a posterior probability, the likelihood that 3I Atlas was artificial given the available evidence. The paper's conclusions were necessarily uncertain because many of the input probabilities were themselves highly uncertain, or unknown, depending on assumptions about the prevalence of extraterrestrial technology and the likelihood of natural processes producing the observed features. The posterior probability for artificial origin ranged from less than 0.1% to as high as 15%. Harrison concluded, while natural origin remains the more probable explanation under most reasonable assumptions, the possibility of technological origin cannot be dismissed as negligible. The anomalous nature of the observations elevates artificial origin from the realm of pure speculation to a hypothesis worthy of serious consideration, albeit one requiring much stronger evidence before acceptance. The paper generated considerable controversy. Some researchers praised it for bringing quantitative reasoning to a question typically dismissed out of hand. Others criticized it for assigning numerical probabilities to fundamentally unknowable quantities, like the prevalence of technological civilizations. Dr. Ellen Rodriguez at MIT published a response arguing that attempting to quantify our ignorance with precise numbers creates a false sense of knowledge where none exists. We simply don't know enough about either extraterrestrial civilizations or exotic natural processes to make the probability calculations meaningful. The SETI community's analysis of their observations appeared in a joint paper published in ACTA, Astronautica, in March 2026. Radio and optical search for technosignatures from 3I Atlas documented the extensive monitoring campaigns conducted by multiple facilities, the null results for narrowband signals and optical pulses, and careful analysis of the sporadic radio. emissions that were detected. The paper concluded that while no definitive technosignatures were found, the observations couldn't rule out the possibility of a dormant or damaged technological artifact, or one using communication methods beyond human detection capabilities. Dr. Sofia Ramirez, lead author of the SETI paper, included a thoughtful discussion of the interpretation challenges. The absence of detected signals is ambiguous. A natural object would show no technosignatures, but neither would an inactive probe, a probe not currently transmitting, or a probe using technologies we don't recognize. Our null result is consistent with all these possibilities and thus doesn't strongly constrain the object's nature. This frustrating ambiguity is inherent to SETI observations of individual objects. We can sometimes confirm artificial origin by detecting signals, but we cannot prove natural origin by failing to detect them. As 2026 progressed and 3I Atlas faded from current observation, attention shifted toward preparing for future interstellar visitors. The Vera C. Rubin Observatory, which had captured the final observations of 3I Atlas, was projected to detect dozens or possibly hundreds of interstellar objects over its operational lifetime, beginning in 2025. With its wide field of view and high sensitivity, Rubin would likely discover several interstellar visitors per year, providing a statistical sample that might reveal whether 3I Atlas was truly unique or representative of a broader population. Plans were developed for rapid response protocols to maximize scientific return from future interstellar visitor discoveries. These protocols included automated alert systems to notify the global astronomical community within hours of detection, prioritized access to major telescopes for confirmed interstellar objects, standardized observation templates to ensure comparable data collection across different facilities, and established communication channels for coordinating international campaigns. The experience with 3I Atlas also influenced thinking about potential future space missions. While intercepting 3I Atlas itself had proven impossible, NASA and ESA began conceptual studies of standing interstellar interceptor missions, spacecraft pre-positioned in the outer solar system with sufficient propellant and maneuverability to quickly redirect toward newly discovered interstellar objects. Such missions would be expensive and might wait years or decades before a suitable target appeared, but the scientific payoff from close-up study of an interstellar visitor would be enormous. By mid-2026, the scientific community had reached an uneasy equilibrium regarding 3I Atlas. The object's hexagonal geometry and other anomalous features remained unexplained, but the initial shock had faded into acceptance of ongoing mystery. Researchers continued analyzing the data, publishing refinements of measurements and new theoretical perspectives, but the pace of new discoveries had slowed. The conversation had shifted from "what is it" to "what can we learn from not knowing what it is?" The philosophical implications of 3I Atlas extended beyond its immediate scientific mysteries. The object served as a reminder that despite humanity's impressive scientific achievements, the universe retained the capacity to present phenomena that defied current understanding. This lesson had value beyond astronomy. It spoke to the importance of intellectual humility, the necessity of remaining open to unexpected possibilities, and the dangers of premature certainty. Dr. Jennifer Park, a historian of science at Harvard University, published an essay examining 3I Atlas in the context of scientific revolutions. She noted that throughout history, anomalous observations that initially seemed inexplicable eventually led to paradigm shifts. The precession of Mercury's orbit helped confirm general relativity. Anomalous spectral lines from distant galaxies revealed the expanding universe. unexpected planetary motion led to the discovery of Neptune. Whether 3I Atlas would ultimately prove similarly revolutionary remained unknown, but its role in challenging established models was already valuable. The public's memory of 3I Atlas gradually faded as new events captured attention, but the object left a lasting cultural mark. References to the hexagon comet appeared in popular media for years afterward, serving as shorthand for profound mysteries and the limits of human knowledge. Science educators used 3I Atlas as a teaching example of how science approaches the unknown, not with immediate answers, but with careful observation, rigorous analysis, and honest acknowledgement of uncertainty. For the researchers who had devoted months to observing and analyzing 3I Atlas, the experience left mixed feelings. The excitement of encountering something genuinely unexplained was tempered by frustration at the inability to reach definitive conclusions. Many expressed hope that future interstellar visitors might provide additional context. If 3I Atlas proved to be one example of a broader class of objects with similar characteristics, comparative study might reveal patterns not visible from a single case. As 3I Atlas continued its silent journey back into interstellar space, moving beyond 380 million miles from the Sun by mid-2026, and continuing outward, it carried with it humanity's questions, speculations, and wonder. The object would travel for tens of thousands of years before approaching another stellar system, assuming it survived the journey. Perhaps someday, inhabitants of that distant system would observe this mysterious visitor and wonder about its origin, just as humanity had wondered. The final scientific assessment of 3I Atlas, published in a review article in Annual Review of Astronomy and Astrophysics in late 2026, attempted to summarize what had been learned. The authors cataloged the confirmed observations: geometric structure with hexagonal symmetry maintained to extraordinary precision, dimensions of approximately 2.6 miles per edge, angular deviations from perfect geometry of less than 0.3 degrees, surface smoothness exceeding that of any known natural solar system body, organized magnetic field of unexpected strength, unusual chemical composition suggesting cold interstellar formation, stable rotation despite asymmetric outgassing, and various other anomalies. The review article's conclusion captured the state of knowledge. 3I Atlas represents either an extraordinary natural object formed through processes not yet understood, or a phenomenon outside the scope of natural formation altogether. Current evidence does not permit definitive determination between these possibilities. The geometric precision, surface properties, and multiple anomalous characteristics challenge natural formation models, yet no alternative explanation has been demonstrated conclusively. The object reminds us that the universe may contain phenomena beyond current scientific paradigms. Whether 3I Atlas ultimately expands our understanding of natural processes or proves to represent something else entirely, it has already served the valuable function of revealing the boundaries of present knowledge and inspiring efforts to expand those boundaries. And so the mystery of 3I Atlas remained, perhaps to be resolved by future discoveries, perhaps to endure as one of those rare cases where nature, or something else, had created something that human science, at least for now, could not fully explain. The hexagonal structure continued its billion-year journey through the galaxy, carrying its secrets into the cosmic night, leaving behind only data, questions, and the enduring human capacity to wonder at the universe's mysteries.